Thank you. We are Team UnifAI, and our mission is to accelerate rare disease diagnosis. We have a case of a study of twins and who were diagnosed with cerebral palsy. They had about 80 tests done, and they suffered for several years as their parents searched for answers. Their parents believed that gene sequencing would help find the answer, and they would save their lives. And it did. At age 12, whole genome sequencing discovered that the twins had dopamine responsive dystonia, and this was treatable with L-DOPA and a serotonin precursor. 80% of rare diseases have a genetic basis, and it takes an average of 8 years to be correctly diagnosed. Misdiagnosis not only leads to a long-term suffering of patients and families, but also incurs a huge cost to patients, institutions, and insurance companies.
So our solution leverages machine learning. Right there. You can just hit play. Sorry. So our solution leverages machine learning. We developed this shiny web app, and each point here represents a distinct disease that's clustered by their symptom etiology. For clinicians, what this means is these are diseases that are typically misdiagnosed for each other. And what's incredible about these clusters is that we can create genetic screens that are specific to disease clusters. In this way, we can create genetic screens that are tenfold cheaper than the current diagnostics available. And we can create this user-facing app that exposes patients and clinicians to our genetic tests. And what's really important about this app is that it allows patients to sort of input their own symptoms and get potential diagnostics associated with them. And this allows the patients to identify potential tests that we can provide for them, or clinicians who are looking for genetic tests to determine what is the genetic cause for their disease. Additionally, we can capture longitudinal data and perform time series analyses.
So the way we'll penetrate the market is by partnering with rare disease foundations, piloting at an institution like Sinai to demonstrate traction and clinical success. From there, we can scale by getting buy-in from insurance companies because they're spending at least $3,000 of wasted cash on this misdiagnoses, on unnecessary clinician visits. So our solution would cost them $350. And that would save them about 10 times the cost of going through this process of 8 clinician visits and misdiagnoses. So looking at the landscape, there are ML-based companies, there are genomics-based companies, and there are companies right in between. So we actually fall on the far end of the spectrum using our two-pronged approach to combine both ML and genetics. Also, we're in a unique niche, our rare disease market. We have patients inputting data for their symptomology and their disease progression, which is unique. And on top of that, we can leverage our intellectual property and our distribution channels to get high market share. Thanks.
So you mentioned that you're 5 times cheaper than whole genome sequencing. Can you talk a little bit about what you envision you would have, what burden of proof you would have to show that you would provide the same information for that dramatic cost reduction?
So in general, whole genome sequencing costs about $1,500, and the analysis costs at least that much more, so a total of maybe $3,000 per person. And in our case, we're leveraging machine learning and clustering algorithms to cluster our diseases according to symptoms. So we bring down the list of potential diseases that the person could have, and we will have specific SNP arrays or chips designed for those diseases. So instead of testing for all 7,000 diseases, we test for maybe like 1/6 of them based on their symptoms. And this genetic test is not an unbiased whole genome sequencing approach, but a more targeted approach that will test for specific mutations that these diseases are known to be associated with already. It also helps the patient to narrow down, it helps the clinicians to narrow down the list of diseases that they should test for, and then we'll give a confirmatory result based on the genetic testing.
So one of the challenges is how does your clustering overlay with actually non-rare diseases, which have a lot of the overlapping symptoms, right? So that's one of the challenges is people think about the non-rare diseases that align with symptoms first.
Right. So to explore this opportunity, we actually mined both NCBI disease taxonomies as well as rare disease taxonomies as well. And we can see the overlap between shared symptomatologies for horses, as one way say, the more common diseases and the rare diseases. And we can take representative cases from very common diseases, if nothing else sort of fits, and then overlay it to our rare disease targeted clustering. Thank you.